Hello viewers and welcome. In our lesson today we are going to look at the velocity time graph. And to help us do that we have selected the SSC 1994 question on the velocity time graph. For the first part of the question we are not going to consider that because it is not part of the task that we have for today. We are going to look at the B part. So let us go through the question and then quickly get into action. So the question reads, a body starts from rest and attains a velocity of 40 meters per second in 20 seconds. It maintains this velocity for 30 seconds and then comes to rest in 25 seconds. I. Sketch the velocity time graph for the motion. I. Calculate the acceleration of the body. And then I. Calculate the total distance covered by the body. Okay, so this is the problem that we have at hand, which we have to find the solution to. So let us sketch our velocity time graph. We draw our ordinate and then our abscissa, that is our vertical axis. We label it velocity meters per second, right? And then our time axis, we label it nicely. Our origin is 0. The object started from rest. Our origin is 0. Okay. So the object started from rest and attains a velocity of 40 meters per second in 20 seconds. So it started from 0. This was where the object was. And then it attained a velocity of 40 meters per second. In how many seconds? In 20 seconds. So we come to our time axis and then we look for the 20 seconds. We go to our velocity axis and then we look for the 40. And then look at where these two particular readings meet. So from there, we draw a straight line from that point to our origin, 0. So the object used to be here, now the object is here. So at that point, what did the object do? It maintained that particular velocity for the next 30 seconds. So at this point, the object didn't increase the velocity, it didn't reduce it, it maintained it. So at that point, we have constant velocity. Acceleration is 0. When velocity is constant, there's no acceleration. So the acceleration there is 0. And then for how many seconds? It maintained it for the 30 seconds. So we count our 30. But we don't write the 30 seconds. We add the 30 to the 20 and then we get what? 50. So we write our 50 here. And then move along that particular axis. And then where these two meet, we join them. And then it finally comes to rest in 25 seconds. So we look for 25 seconds. We don't write the 25 seconds, we add the 25 seconds to the 50, and then that gives us 75. And then from there, we join. Okay, so now this is where the object is. So we have like 3 sections. The initial acceleration, the constant velocity, and then the deceleration, retardation, or the negative acceleration. So we have 3 sections, like section A, section B, and then section C. So this is the velocity time graph. Very simple. This is the velocity time graph that we have. The second part is that we should calculate the acceleration of the body. So acceleration A, v minus u over t, where v is final velocity, u is initial velocity, and t is the time taken for the object to move from the initial velocity to the final. That is the time consumed between these two particular velocities. So v, the final velocity, is 40, u, my initial velocity, is 0, and t, the time consumed, is 20 seconds. So this gives me 2 meters per second squared. So final velocity of 40, initial velocity of 0, and the time consumed of what? 20 seconds. So that gives me an acceleration of 2 meters per second squared. Then my third part, I have to find the total distance covered by the body. The total distance covered by the body. For a velocity time graph, the total distance covered by the body is the area under the graph. So we are coming to use the area under the graph to find the total distance covered by the body. So our task is to find the total area under the graph. If we look at the graph, we can see it's in 3 sections, section A, B, and C. This is a triangle, this is a rectangle, this is another triangle. So we can calculate the area of a triangle, that of a rectangle, that of a triangle, add together, we'll get the total area, and that will be the total distance. Or we can look at the whole figure as just a single figure, the whole graph as a single figure, like a trapezium, and then use the formula and then calculate the area of a trapezium, and then bam, we can also arrive there. And when we finish, we can use equations to cross-check and see if our calculations are right. Okay, so let's go this way. So my first part is a triangle, my second part is a rectangle, and my third part is also a triangle. So here, what do I have? I have half breadth times height. So my breadth is 20 and my height is 40, plus my length and my breadth, that is 30 times 40 plus 25 times 40. So this gives me 400, this gives me 1200, and this gives me 500. So I have 2100, right? So I have 2100. All right, so this is what I have. I have 2100 as my total distance. Now let us use the formula for the trapezium and see what we are going to get, just to cross check and see. So if we say total distance, so we have this. So the longest side 75, the shortest side is 30, right? Times my height, which is 40. So this gives me 105. So this gives me 2100. Yeah, just that. Okay, so we are right. So to cross check the total distance along this route, what do we have? The total distance along that route, what do we have? So to use formula, I'm going to have SV squared minus U squared all over 2A. So I have my final velocity there is 40. My initial is 0. So 40 squared minus 0 squared all over 2 times 2. And what does that give me? That gives me 400 meters. Yeah. Now for the second part of my journey, what I have is it's a constant velocity section, and if the velocity is constant, I'm not going to have acceleration. And if there is no acceleration, then what it means is that this particular formula is not applicable. I can't apply this formula because of the absence of acceleration. So I have to go with a different one. So distance is called velocity times time. So my velocity is 40, and my time for that particular section, the total time consumed for the section is 30. So this gives me 1200 meters, correct? And then for my last part, I can apply this formula again. All right, but the problem here is that I don't have the acceleration for that part. So I have to find the acceleration for that part before I can be able to use that formula. So let us find the acceleration here. So the acceleration here, my final velocity is 0. It came back, it started from 40 and then came down to 0. So my initial is 40, my final is 0, and then the time between the two is 25, right? So this gives me negative 1.6 meters per second square. So negative 1.6 meters per second square. So that is the deceleration, retardation, or the negative acceleration there. So that is the acceleration along this route, but it's negative because the object is coming to a stop, right? So if an object is coming to a stop, its acceleration is negative. That's why we have the negative value there. So now that I have my acceleration, I can come back and then put it in here. So my final velocity there, 0. My initial there is 40 all over 2 times negative 1.6. So when I do that, I'm going to have 500 meters. So we cross check. So when we add this, this, and this, what are we going to get? We are going to get 2,100 meters. So we are back to the same answer that we got when we used the graph. So we use the formula to cross check the graph, right? So this is how we approach it. Not so difficult. Once again, not so difficult. You only have to know what you are doing, how to approach it, the various components that is required, and the things that you are expected to do. So acceleration, positive along this route. Acceleration here is negative. That's why we refer to it as negative acceleration, retardation, or deceleration. Acceleration, no. Along this route, acceleration, no. There's no acceleration. Why? Because velocity is constant. Anytime velocity is constant, acceleration is 0. So no acceleration. All right. So we did that, and then we had our total distance, and then we used the formulas to cross-check, and then we saw that, yeah, everything is intact. So this is how we go by the velocity time graph. This is the lesson 1. We've done some work. In lesson 2, we are going to look at a case where the object stopped and then it's reversed. So we are going to have 2 directions, a positive direction and then a negative direction. This is just in one direction. So we can say this is just one direction, this is a positive direction. So the object stopped. All right? No, so in our second case, we can say, yeah, the object stopped and the driver decided to reverse back. So that is going to be against the original motion. So that's going to a negative motion. In that case, we are going to have distance and displacement being different. In this case, distance and displacement are equal, because this is where the object started from, this is where it is. So with respect to the starting position, the distance, the total distance is 2,100 meters, and the displacement is 2,100 meters with respect to the starting position here. All right, good. But if the object reverses, then we are going to have a different case. The distance and the displacement may not necessarily be the same anymore. So this brings us to the end of our lesson. Remember, if there's anything you want to ask or say, go to the comment section, put anything that I'll try as much as I can to get back to you. All right, and then subscribe, leave your comment, like, share, and then I hope you have enjoyed the lesson. Until I see you in my next video. Remember, as always, take care of yourselves and each other. Cheerio and fit it. Bye bye.